One bourbon, one scotch, and one bill. One bourbon, one scotch.
Okay, so now for the next kind of transformation we can do to functions called reflections, okay? Or reflections, we'll call it. Okay, so again, for the first kind, we have vertical reflections, okay? So vertical ones, again, like everything else that has to do with things that are being transformations that are vertical, then our reflection happens to the output, okay? So we have our normal f of x, and then we multiply by a -1 for some reason. Okay, and what this does, what this has the effect of doing, is reflecting things vertically. So that means like up or down. Okay, so what this does is it kind of flips the sign of our output. Okay, so let's look at what would be an example of a graph that's reflected. So that would be like -x squared. Okay, in the sense that this negative sign isn't attached to our x, but it's kind of like you would have had parentheses here. So you do the exponent first, and then you account for the sign. Okay, so let's see what this does. So normally our x squared graph looks like this. So we have 1, 2, 1, 2, 1, 2, 3, 4. So normally it looks something like this, like a U, right? Pointing up. So this is the positive x squared graph. But now that we have this negative sign in front, we're going to take all of our outputs. So for example, 0, 0 will turn into 0, 0. So nothing exciting there. But now instead of the point 1, 1, 1, comma 1, when we plug in a 1 here, we're going to get out a -1. So it kind of just flips all of our points down below or across the x-axis, okay? So if you plug in a 2, for example, we're going to get a -4 instead of a +4 like we had before, okay? So it just flips the sign of all of our outputs. So we get something that points down instead. So this is the graph of -x squared, okay? So a vertical reflection reflects graph across the x-axis, okay? Alrighty, so now let's look at you guessed it, a horizontal reflection. Let's see what's going on with those. So horizontal, that means we're affecting the input. So that means that instead of the negative sign falling outside of our function, we're actually going to have the negative sign be in there with the x, okay? So it's going to affect our x directly. So what this is going to have the effect of doing is kind of just flipping it across, instead of the x-axis, now across the y-axis, okay? So let's actually try a different graph, okay? Let's say we're going to do square root of x, okay? So, but we want to see, instead of square root of x, now we want to see what happens when we make it square root of -x, okay? So let's graph both of those. So originally we have 1, 2, 3, 4, 1, 2, 3, 4, and then like 1, 2, or something like that. Okay, y and x. So our original square root of x, let me graph that first. So that would be kind of based at 0, 0, and then we go 1, 1, and 4, 2. So it looks like a swish to the side. Okay, so that's our original square root of x, square root of positive x, that is. Okay, so now let's see. Okay, well, now that we have this negative sign in there, then that basically just flips everything across the y-axis. And we know this because, well, 0, 0 just stays there. But when you plug in a -1, per se, then we get square root of -1, which turns it into a +1, which gives us out a -1, comma 1. Okay? Whereas, like, if you were to plug in a 1 into this, it would be undefined because you can't take the square root of a -1. So everything just flips across the y-axis, okay? So let me do that with -4, comma 2, okay? So we get a swoosh that looks like this instead, and this is the square root of -x. So it reflects, so a horizontal reflection reflects across the y-axis, okay? All right. So we have that reflecting across the y-axis. So let me actually, on the next slide, I'll try to do another horizontal reflection, and we'll see something that goes a little bit fishy. Okay, so here's going to be an example of horizontal, if I can spell, hold on, horizontal reflection attempt, basically. Okay, so let's say we have the function f of x is equal to x squared, okay? And then we want to graph, well, we're going to graph this first, and then we'll graph what should be the horizontal reflection of it, right? Because we added that negative sign in with the x, like directly connected to it, okay? So let's graph these two. Let's see what we get. So we have 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Okay, so here's our y axis, and there's our x. So our normal f of x graph looks kind of standard, right? This is becoming second nature to us now, graphing these u's here. Okay, so this is our original, well, not our original, but this is our f of x. Okay, so this is x squared. And then if we do the same thing but with g of x, now we're going to be flipping all of our points across the y-axis, right? Because that's what a horizontal reflection is. So if we flip all of our points across the y-axis to get our g of x, we end up with the same curve, right? Because if you reflect 1, 1, for example, this point across the y-axis here, it becomes negative 1, 1, which is already a point on our graph, right? So in this case, because we have that squared here, the horizontal reflection basically just gives us back the same exact graph, okay? And there's a special name for this. So that would be called, let me start a little section here, a new section. Then we have what's called an even function, okay? So what's the definition of an even function? These are basically special graphs for which when we have f of x is equal to f of negative x, okay? So that just means that we are already symmetric about, this is just fancy language, but symmetric about the x-axis. That just means it doesn't matter whether you're on the left side of the y-axis. That doesn't mean if your x is negative or if your x is positive, but if you have the same absolute value, then you have the same output for your function. Okay, so here's another example. Let's look at f of x is equal to absolute value of x. I kind of just alluded to that in the previous statement. Anyways, so in this case, we have x and y, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so 0, 0 is a point, and then 1 gives us 1, 2 gives us 2, and 3 gives us 3. Okay, that was a really bad line. Anyways, so we have something like this on the right-hand side, and then when we look on the left-hand side, when we plug in a negative 1, we still get out that same value of 1 that we got when we plugged in a positive 1, okay? Because we do have that absolute value sign, which is pretty nifty, so we have the same exact thing happening on the left side. Whatever's happening on the left side mirrors what's happening on the right side. So therefore, that just means we're symmetric about the x-axis. Thus, we have an even function, okay? So as we can see, this is going to be the same thing as f of negative x. These are going to be equal to each other because we have that absolute value sign, which kind of just disregards that sign there, okay? All right, on the other hand, we have something which is called an odd function, and we'll go over that on the next slide. Okay, what is an odd function? Well, okay, so an odd function is defined if we have f of x is equal to, and as the name kind of implies, it is a bit strange, it's a little bit odd, but f of x is equal to negative f of negative x, okay? So it's like, whoa, what's going on here? We have too many negative signs. Can we just cancel them out and make positive? And the answer would be no. Sorry about that. But anyways, let's see what's really going on. So inside here, because we have the negative sign connected directly to the x, this is a horizontal reflection, right? So here's a horizontal reflection going on, and we have a negative sign on the outside. So this is a vertical reflection. Vertical reflection. So basically what this means is that, okay, a function is odd if we can do a horizontal reflection and a vertical reflection and get back to the same place, okay? So this is what's called symmetric, not about the x-axis, but about the origin, okay? And again, this is just kind of terminology. So yay if you know it, it's not really a big deal if you don't know the actual terminology. So let me show you an example of an odd function. So a good example is f of x is equal to x cubed, okay? So the x cubed graph, let's look at that. So we have 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 0, 0, and then we have the point 1, 1, negative 1, negative 1, negative 2, negative 8. I'm moving the screen instead. Okay, and then positive 2, positive 8, somewhere up there. So it's like this huge S thingy curve thing. Okay, so it looks like that. That's our original graph. Okay, and now let's see, well, if we have negative of negative x to the third. So here's our horizontal reflection going on, and here's the vertical reflection, right? Then we have something that looks like this. So let's do actually one step at a time, okay? Let's actually go back, and I'll show you how it gets there. So let's do the horizontal reflection first. So let's do negative x to the third power. Okay, so if we graph that, and then we'll have 1, 2, 1, 2, 1, 2, 3. Pretend this goes up to 8, and pretend this goes down to negative 8. Okay, it's just the concept. So 0, 0 just stays there. All right. But if we were to plug in a 1, now we would get negative 1. Right. If we were to plug in a 2, now we get a negative 8. Okay, so it kind of just flips this about the y-axis. Remember, that's what a horizontal reflection does. Okay, so now we have this graph that looks like kind of a backwards S thingy. Okay, so it flipped it about the y-axis. And now if we stick an extra negative sign on the front there and do the vertical reflection, we could see that it's just gonna, these negative values are gonna become positive, and these positive values are gonna become negative, and we're actually gonna get back to something like what we started with. And we're actually going to get back to something exactly what we started with. So that would be 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. So we're going to get back to that original S that we had in the beginning. Okay? And again, this thing here, that's an example of what an odd function is. I know, it's a little bit odd. Okay, so the last thing is I'm just going to point out that, well, if things aren't complicated enough, and you haven't learned enough, we can always combine transformations, okay? So that means, like, okay, when we have x squared, we can't just add positive 2 onto it. What we can do is also multiply by a 2 at the same time, and then we have more complicated things. Yay! So anyways, so what we're going to do now is combine transformations. Combine transformations. Okay, so in this, I'm just going to kind of delineate in the steps in which you do things. So if you combine vertical transformations, for example, so let's say if you combine vertical things, so that would be like saying a constant times f of x, our function, and then you just tack on that k, okay? So in this case, what we have going on is a vertical stretch or compression, and then we also have this vertical shifting. Shifting, and this would be up or down, right? Because that's what the whole vertical thing means, okay? So the first thing you would account for is the vertical stretching or compressing, okay? And then you would account for the vertical shifting, up or down, okay? And then as for horizontal, if you have multiple things going on here, what this would look like actually is, because everything happens to the input when we have horizontal transformations, right? So we have our b times x, and then our minus h here, right? So you have something like that going on. Or you could consider it a positive h, and then just kind of like subtract things. Anyways, I'll just put this here. So then what's going on? This is our horizontal stretch or compression. Okay, and the h is our horizontal shifting, left or right. But what's really important to notice here is that this h here, don't take it by itself. What we have to do is actually take this b and factor it out. Okay, so this is kind of a difficult part, because it's, like I said, like we've seen the trend throughout explaining shifting and stretching or compressing and reflections and all of that, that horizontal tends to be a little bit more complicated than vertical in any case. So for this, what we have to do is say f of, and whatever your b is, you're going to factor it out of both terms. So b times x, and then when we factor out the b, then we divide by b on the inside. And you can just check that by redistributing it back in, and then you'll get back to the same thing. But anyways, so what this means is that the horizontal stretching and compressing happens first. So this b thing, this horizontal, whether you stretch or compress, that happens first. And then you take this h over b, okay, and that itself gives you the horizontal shifting either left or right, okay? So this is really important down here on the bottom. And we'll do examples in the practice problems video, okay? Alrighty, so that wraps up our concepts video on transformation of functions. I hope that helps, and I'll be talking to you if you watch the practice problems video.